All right, welcome back to the effect. We're still talking about regression discontinuity, and in particular, how can we estimate a regression discontinuity effect? We've got this idea about regression discontinuity. We have a smoothly changing running variable that at some point comes to a cutoff where a treatment is applied. Just because you are just barely over the cutoff, you get the treatment, and if you're just barely below it, you don't. And by comparing people within that narrow range around the cutoff, we think that we are isolating some source of exogenous variation that we can use to identify an effect. Now, there are many ways to estimate a regression discontinuity effect. As I keep saying, the research design and the estimation method are not the same thing. There are often many different ways to estimate a given research design, and often the same estimation method can apply to different research designs depending on context. But let's talk about the simplest approach to estimating regression discontinuity, which is just to use linear regression. It's back. So in particular, we can use a linear regression model that looks sort of like this. So what do we have here? We are regressing our outcome y on the running variable minus the cutoff. I'll talk about that in a second. We also have an indicator for being treated, which is being on the correct side of the cutoff to be treated or not be treated. It's a binary variable. And then we have the interaction between the running variable minus the cutoff and being treated. So when we look at this, we are effectively estimating two lines. We are getting one linear regression to the left of the cutoff and a different linear regression to the right of the cutoff. In particular, if we set treated equal to 0, so you're on the untreated side of the cutoff, we have an intercept of beta 0 and a slope on the running variable of beta 1. How about if we set treated equal to 1, so we're on the treated side of the cutoff? Well, in that case, we have an intercept of beta 0 plus beta 2, and we have a slope on the running variable of beta 1 plus beta 3. And that brings us to why we're using running variable minus the cutoff instead of just the running variable. What I'm doing here is I'm taking whatever my running variable is. Perhaps I'm looking at the income that you have relative to the cutoff that lets you qualify for maybe some sort of income relief, and I'm subtracting out the cutoff. So let's say if the cutoff is $12,000 and you earn $12,005, well then your running variable minus the cutoff would be 5 because you are 5 above the cutoff. So why am I doing this? Well, what this does is it makes sure that the running variable, after you subtract out the cutoff, is 0 at the cutoff. Why might that be useful? Well, let's think way back to our regression stuff and think about our interpretation of the intercept coefficient. What is the intercept? The intercept is our prediction of the outcome when all the other predictors are at 0. So if we set the running variable to 0, then the intercept is our prediction at 0. Great. And by setting it so that the value of the running variable is 0 at the cutoff, that means that our intercept now gives us our prediction at the cutoff. Why is that handy? Because that is the point at which our two lines meet. Let's look at this graph. So clearly the fit here is not great, and I'll talk about that in a bit. But what's happening is I fit one single regression line to the left, and I fit a different regression line to the right. And if you look where they meet at the cutoff, that's going to be our two different intercepts for our two different lines. The line on the left side is leading up to that dashed line, and the point where it hits the dashed line is the intercept for the line on the left. Similarly, for the line on the right, the point where it's pointing at that dashed line is the intercept for the line on the right. These are, respectively, beta 0 and beta 0 plus beta 2, which means if we're looking at how things changed at the intercept, if we're looking for what jumped when we hit the cutoff where the treatment went into effect, right? Running variables smoothly changing, smoothly changing, smoothly changing. Cutoff happens, we expect a change, right? How big is that change? Well, it's the jump from one line to another. Or in other words, the change from one of the intercepts to the other. So if we're going from beta 0 to beta 0 plus beta 2, that means that our coefficient of interest, the regression discontinuity effect, is beta 2, because that's how much our intercept changed when we went from the untreated side to the treated side. So this is the simplest way of estimating a regression discontinuity model. We simply fit a line to one side of the cutoff, and we fit a different line to the other side of the cutoff, and we see where they meet in the middle. Now you might notice if you watch the event study videos that mathematically this is the exact same thing as our interrupted time series approach to estimating an event study, or at least what I called an interrupted time series approach with linear regression. There's a reason for that. Mathematically, event studies and regression discontinuity are basically the same thing. They're just different research designs. In one case, with the event studies, we could sort of say that our running variable is time, and in a regression discontinuity, our running variable is something else that is not time. Now, why do I consider those to be two entirely separate research designs? Well, because the assumptions that you need to make this all work are very, very different depending on whether the running variable is time or not. It's simply a much different assumption to say that people just before and just after an event within a narrow window are basically the same and comparable, as opposed to people on one side of a cutoff or another. It's just the idea that we're sort of randomly falling on one side or the other makes a lot more sense with most running variables that are not time than it does with time. You can't really randomly be before or after. And so that doesn't work in quite the same way. And in general, people would say that regression discontinuity is a lot more plausible than event studies for that reason. The assumption that you need to make that just before to just after is basically a random comparison is a lot more plausible for running variables that are not time-based. So that's why we think of them as two entirely separate research designs, even though mathematically there are a lot of similarities. So this basic two-line regression equation is more or less it. It's a simple way of estimating a regression discontinuity. Now, there's a lot of other stuff that might go in here. In particular, I talked about the bandwidth. We're focusing in just on the narrow area around the cutoff. That means that when we are estimating these lines, we need to worry, hold on a minute, didn't I just bring back in all the data that was far away from the cutoff? Well, yeah, that's sort of what we did here. We used the entire range of data to estimate these lines, which might not be what we want. And so one common thing that you might do with these regression models is to narrow your range, either dropping data that is far away from the cutoff, saying, I think that maybe within this particular bandwidth, yeah, maybe that's comparable. Using our income example, maybe I'd say, okay, I think that people who are earning between $11,900 and $12,100, those people are close, have their incomes close enough that I would believe that they're basically comparable. And then I'd limit the data to that and fit the regression lines just within that data. So you might limit your sample using a bandwidth before you estimate this model. And of course, there are other ways to make the same sort of idea, where we're emphasizing more the data that's close to the cutoff as opposed to the data that is far away. I'm not going to go into all the different ways that we can do that to focus in on the data that's just around the cutoff and get rid of the data that's far away. I'll talk about some more in the next videos, but we do have a sort of trade-off here. And this brings us to the statistical power issues that I mentioned last time when I was talking about regression discontinuity. The problem with regression discontinuity is that you're saying, hey, I really only think that we have identification in this narrow stripe of data just around the cutoff. And that's a problem because if you just focus in on the narrow stripe of data just around the cutoff and you drop everybody who doesn't have an income between $11,900 and $12,100, well, you're dropping a lot of your data, which is going to make your estimate really noisy because your sample is going to get super duper small. So there's a trade-off, right? The narrower in you focus around the cutoff, the better belief you might have about your causal identification, and we might say that you might have a low bias estimate. But you're also going to be very imprecise because you're dropping a lot of observations, you're making a very small sample to do your analysis with. If you allow in more data on either side of the cutoff, well then you're getting more precision because you have more data, but also you're bringing back in some observations that have maybe less comparable values. You're saying, I'm going to widen my income range here to compare people who have $13,000 of income against people who have $10,000 of income. Is that really comparable? Maybe, maybe not. Maybe we start to lose our belief in the identification at that point. We think that some of those vector variables might be coming back in. So there's a trade-off in terms of how wide you make your bandwidth. Additionally, there are some other considerations that we might make in terms of how we do this model. So you notice that I had this graph before, and clearly the fit there is not very good. You don't have to use a linear regression on either side. You could use a curved or polynomial regression on either side to better fit the shape of the data. In particular, you could use a squared term and a quadratic to your model. You probably don't want to go beyond that for reasons I discussed in the chapter, but you could fit this data a lot better. It might look like this. And that is something you want to keep in mind. You do want to pick a functional form that fits your data pretty well because otherwise you're not going to do a very good job at telling where the data is going to hit that dashed line, which is our real goal, right? We want to really see where that line is going to hit. Which if you look at the original data, you can see that that data is hitting the dashed line at a very different point than the fitted line does. So adding the polynomial term in this case would really improve our idea of what the estimate actually is. And adding this polynomial term is super duper easy. What did we have before? We had the running variable minus the cutoff, and then we interacted that with whether you're on one side of the cutoff or another. Done. For a polynomial term, you just have the running variable minus the cutoff minus the cutoff squared, and then you interact that with whether you are above or below the treated cutoff. That's it. You're done. Very good. So we talked about how we want to consider maybe the functional form. Maybe you want to have a curvy line to fit. There are some other ways we can add some curviness in there I'll talk about in future videos. We also talk about picking the bandwidth and the sort of pros and cons of picking wider or narrower bandwidths. And there are also, by the way, some procedures out there that you can use that are called optimal bandwidth selection to select how wide you want that bandwidth. You might also just try a bunch of different bandwidths and see whether your results are stable as you get bigger and bigger bandwidths and thus more and more precise estimates. If it looks like your estimate itself doesn't change that much as you bring in more and more data, then you might as well bring it in because it doesn't seem like it's biasing you all that much. One other thing I want to say about estimating regression discontinuity is what do you do if the cutoff does not perfectly determine your treatment? I'm not going to talk a whole lot about fuzzy regression discontinuity in these videos, for a lot more in the chapter, but what fuzzy regression discontinuity is when you have a running variable that only partially determines your treatment. So for example, let's go back to that income example with the income relief. Let's say that if you are below $12,000 a year, then you qualify for this income relief program, but you also have to apply for it, and not everybody's going to apply. So instead of going from 0% treated above 12,000 to 100% treated below 12,000, you might get 0% treated above 12,000 and 50% treated below 12,000. Well, how do you deal with regression discontinuity in that case? Well, we have to adjust our estimate, otherwise we're going to get things wrong. But it's actually pretty easy to do. All we have to do is bring in some of our instrumental variables knowledge from the last chapter. Because what do we still have? We still have some sort of randomish assignment being above or below the cutoff, just on one side or the other. That is still going to predict our treatment. And so we can use the being above the cutoff as an instrument for actually being treated. I say, hey, your income is just below 12,000. That's going to increase the probability that you are treated. And then I will use that predicted increase in your treatment probability rate to see what the effect of treatment is on your outcomes. Look in the chapter for more technical details on that, but that's basically what we're doing. We're taking all the instrumental variable stuff we did from last time and just applying it with regression discontinuity, where being on one side of the cutoff or another is an instrument for being treated or not. All right, that is it for some basics on estimating a very basic version of regression discontinuity. There'll be some other variants we'll talk about in future videos. Thank you.